Hello. Waving from the Fluno Center. Okay, we're going to get started with our second session of the morning with some more talks from CHUC researchers sharing about their work and their experiences with computing. So I'm pleased to introduce Megan Frayer, who's a Ph.D. candidate in genetics, and she'll be sharing about genomic ancestry in mice, and I'll let her take it from there.
All right. Hi, everyone. You can all hear me well, right? Okay. All right. So excited today to tell you a little bit about my work. If my slides, there we go. All right. So as Christina just said, I'm a PhD student in genetics, and I'm really interested in the genetics of speciation. So very basically, that's just the process by which one taxa becomes two separate taxa that are no longer able to interbreed together. And I'm really interested in the genetics that underlie that process, both how they become separated and how they maintain that separation. So I'm focused on house mice, and so in house mice, there's a huge hybrid zone that is very well studied that runs through the center of Europe. So we have subspecies Musculus on one side and Domesticus on the other, and we can think of each of these as having their own sort of unique genetic background that we call ancestry. And we can identify from the genetic sequences what ancestry a specific piece of DNA belongs to. And the hybrids that come from this hybrid zone have a mixture of these two background ancestries. So that's what I'm really interested in, is identifying those patterns and what they can tell us about speciation. And so what this sort of looks like at a very fine scale, is we have a genetic sequence and we compare it to the parental sequences that we have available and try to identify the places where the background of the hybrid switches from one to the other. And we call that place a junction. And so that's really what I'm focused on identifying. And just to give you an idea, this is sort of what it looks like at a broad scale. This is a single chromosome where each bar is a different individual, and just kind of showing how mixed up their genetic backgrounds are. So this gives us a very large data set to work with. But overall, the things that I'm doing in my research are very computationally basic, but slow. So one thing that I wanted to do is just very basic parameter grid search, where we're looking for, so when we do that inference that I just showed you, there's a number of assumptions we have to make and in the program. And so we want to find the combination of input parameters that has the highest likelihood, because for some parameters, we have a better sense of what they should be than others. Now this program has a lot of parameters, and what these parameters are and the numbers don't really matter for this moment, but the key thing is there's a lot of potential parameters, and there's therefore a lot of combinations. And so in total, I was interested in looking, in this particular case, interested in looking at 108,000 combinations of parameters. Now the program says that, the best practice would be to look at some different parameters, and it recommends maybe 3 at a time. Because this program, we're looking at a lot of data, it's very slow. But, I want to do better than that and look at all these different combinations, because for some of these parameters, we really don't have a good sense of what they should be. And so that is where high throughput computing comes in. So essentially what I'm doing is a pretty simple basic pipeline of creating input files, running these different independent parameter tests and then compiling the results to compare them. And that running these independent parameter tests is really where the high throughput computing comes in. So just to give you an idea of how I'm running it, again, this is all very basic. So we have an overall DAG where the first step is to create input files. And I always have that as my first step. And so I'll have a script that can print submit files, executables, the input for the program that I need to run. And I find that this is really helpful for reproducibility because if I want to go back and run maybe a different set of parameters or look at a, make some tweak to the program, I can just make that tweak and then easily reproduce all of the submit files that I need for each individual instance. So from those input files, the next step is to run all of these parameter tests in parallel and then bring them all back together to just create a big table that I can then, pull out and do comparisons with. So very basic DAG structure. Oh, and I can also, one feature that I've taken advantage of quite a bit is to use a subdag external for this central part, because that actually allows that first step, that create input files, to actually make the DAG itself. And that way I don't have to worry about knowing in advance, how many instances I'm going to run. The first step can decide that for me and then print the DAG that I need to run all of that. And so this is really a fairly basic pipeline, but it really greatly improves what I'm able to do. So running without any parallelization, it takes about 2 hours per test. And so running on my computer one at a time, it would take almost 25 years to run all 108,000 combinations. But with the CHTC in this particular instance, I was able to run all of these in about 10 days. And it probably would have been faster, except these tests all have a lot of, require a lot of memory, so they queue a little slower, but that's still a pretty extreme improvement. A very similar pipeline that I've run is to look at simulated chromosomes. And so we can do this, we can simulate chromosomes that have known ancestry that can kind of tell us how well that inference program is performing, how well it's calling the ancestry. And so again, we have a pretty simple pipeline where we're just going to simulate chromosomes, determine the true ancestry of those simulated chromosomes, then infer the ancestry using our method, and then compare the true and infer maps to see how well it did. And running these simulations, these are all independent, so that is a great place for high throughput computing to come in and improve our speed. So again, it's a relatively simple DAG. We have the first step of creating input files, and then the input file will determine the submit files for all the different parameter sets I want to run. And then in this case, we can add a little bit of, for each parameter set, I can run it multiple times because, when we simulate things, there's a range of outputs that we can get it doesn't always give us the same thing every time. So that can give us an idea of, confidence intervals and that sort of thing. I can run numerous parameter sets all independently with a certain number of, duplications of each parameter set. And then compile all of that in a final node to just create a big table that I can compare. So this particular pipeline, it takes about 3 hours per test, which to run just 50 tests, which isn't that many, would take about 6 days. But with this particular instance, I timed it took in a total about 10 hours. So again, a really big improvement that gives me a lot more flexibility to explore a bigger parameter space with a relatively simple computational pipeline. Probably the biggest advantage that I've gotten from high throughput computing is in simulations. So I run a lot of simulations to ask a lot of different questions. And essentially each simulation I'm running, all I really need to do is run a simulation program and then run a little script that makes a summary. It's very simple, something I definitely normally do just on my computer. However, the questions that I'm interested in from a genetics perspective require what we call forward simulations. So forward in time, Now, what we call backward simulations or backward in time simulations are very fast. We're talking about running in a matter of seconds. But forward simulations, they're slower, they require a lot more memory, they can take hours as opposed to seconds. So you're really limited in the number that you can run on a normal computer, where you might be able to run your full set of backward simulations. So for simulation DAGs, I usually have them set up like this, where I have just one DAG where everything's running in parallel. There's no connecting nodes. But the reason I run it this way is because that allows me to have variables and template files. So I have one single template submit file, and I generate a DAG that runs, each simulation parameter combination out of the same template file. I can set up a script that can generate the DAG based on whatever parameters I give it. And this is really huge for both speed, but also reproducibility, because if I want to run another set, I can just tweak that initial input, telling it how many I want to run or what parameters I want to run, and it will run it through the same exact submit file. So this is really great. I also can take advantage of these config files, and specifically max job idle. So I can submit millions of jobs without having to worry about overloading the node, because this is gonna only submit 1,000 at a time. So that way I can run my big, huge data sets without having to worry about submitting them in small batches. So that's really a benefit. So I timed one specific set of these where I ran about 12,000 simulations. And again, it takes 2 hours per test. So on my computer, it would have taken about 3 years to run all of those, but I'm able to do it on the CHTC in about 30 hours. So that gives you a sense of just how much more I'm able to get done, even though everything I'm doing is a relatively simple computational pipeline. The other thing that I was able to use with simulations are Docker environments, which using the Docker environments limits the number of nodes that you can connect to, but it again can help with reproducibility, because it makes sure that every simulation is running in the same computational environment with the same libraries available to it, and just kind of expands the options of what I'm able to run. So in conclusion, I think that high throughput computing has really improved my research, and it has the power to improve a lot of research in biological sciences, even things that are, again, relatively simple computational pipelines can be really sped up, and you can open up a lot more opportunities to explore bigger questions by using high throughput computing. Even really simple DAGs can make a big impact on the amount of programs you're able to run, the amount of parameters you're able to compare, all of that sort of thing. I also have found that DAGs are really great for improving reproducibility. I have, a single file that I can change, and it will recreate all of my input files. If I want to, run a different parameter, if I want to increase the number of, replicates from 50 to 100, I can just make that change in one file, and it will reproduce all of my submit files in the same way, which I just think is really great. So in the last year, I've mostly from doing these forward simulations, I've used millions, 8.5 million, roughly HTC hours. So another way to think about that is that I have shortened my PhD by about 1,000 years. So it felt like, 1,000 years, but it wasn't. So that is pretty good. So with that, I will take questions if anybody has any.